Okay, welcome everyone. Nice to see the attendance at this hour, like 7:30 for us, 17:30, 5:30 for us. Burak is a postdoctoral researcher at CMU. He received his PhD in electrical engineering from Rensselaer Polytechnic Institute in 2024. And he actually studied in Turkey. He did bachelor's in electrical engineering, electrical and electronics engineering from the Boğaziçi University in 2018. His research develops theoretical foundations at the intersection of causality and machine learning, with an emphasis on leveraging interventional data and shared causal mechanisms for representation learning, sequential intervention design, and causal structure learning. He is also broadly interested in identifiable representation learning, including self-supervised approaches. He was a recipient of IBM AI Horizons Fellowship during his PhD. And thank you very much, Burak, for accepting our invitation today. We are looking forward to your talk.
And thank you for having me today. I'm very excited to talk about my research. And let me share my screen. So I trust you all see my screen. So hello, everyone. I will talk about the emerging field of causal representation learning today and our work on it. So just to give a very brief background as a precursor to what will follow. Causal representation learning emerged as like a culmination of a couple different fields, like from disentangled representations, independent component analysis, causal inference, and even a few more related fields. And to my knowledge, it started to brew in like late 2020, and the field started to boom off with a position paper in 2021. And me and my collaborators, Emre Acartürk from Rensselaer and Ali Tacar, who was my PhD advisor at Rensselaer, and our longtime collaborator Kartikeyan from Google DeepMind. We've been working on this starting in the second half of 2022, and we had a bunch of work on it since then. So today, instead of trying to give every deep result from different papers, I will try to give a broader summary of like why we care about this field and what is our unique approach to solving the problems proposed in this field and how they might actually solve some real problems. So you can see the links for an incomplete project page that's on my to-do list for a while. And actually recently this summer, Ali gave a tutorial at North American School of Information Theory, like a 2-hour tutorial on this topic. We actually had a AI tutorial as well, but which was not public, I believe. So let's start with the success of representation learning and the connections. Essentially, deep learning replaced the feature engineering part of learning some low-dimensional representations, the feature embeddings from high-dimensional, unexplainable structured data. When I say high-dimensional and complex, for instance, the pixels of an image themselves do not really have much meaning. So instead of deriving, handcrafted features, as in the first wave of the AI, maybe in the 60s with the symbolic learning, deep learning just comes up with an automated process of extracting the essentially latent factors. And in the recent boom of the generative AI, we also see the reverse direction having huge empirical success, where we generate very plausible data by, from embeddings or like the token sequences, essentially going from the latent space to the data space. We have seen very successful applications in the last couple of years. But how do we tell a learned representation of the data is good enough? Essentially, what we seem good enough depends on what do we want out of it. So say if we want the learned representations to be useful for some standard machine learning task like prediction, then if they capture enough structure to form our downstream decisions, we can call them good enough representations. I'm happy with it. Or if my goal is, compressing the data, such that I can reconstruct it in an almost lossless fashion through an autoencoder. Or if I want to generate very plausible images and other modalities of data, then I can say that if these things are possible, then my representations capture enough structure to enable these applications. So it is good enough for me. But I want to look a little bit deeper and ask, is good enough representations, this definition of good enough, sufficient for a strong generalization, for instance, for out-of-domain generalization? To motivate the identifiability angle, I want to give one example from a Google paper from a couple of years ago. So let's take ImageNet datasets and train 50 ResNet models on the ImageNet with following identical pipelines, except only changing the random seed. So the first nice thing is on the ImageNet validation and test data, essentially in distribution test data, then if we look at that performance, it varies very little across different models, which is somewhat suggesting a robustness. And we can be happy with it if this is what we only care about. But if we consider a corrupted version of ImageNet, let's call ImageNet C, where minor distribution shifts are happening, for instance, changing the brightness of the images or the contrast, or lowering the resolution with some pixelation applications, then we can see that the model performance among these 50 models, it can widely differ with respect to the original test performance on the ImageNet data. So if we were, say, learning identifiable features, meaning that if I give the same data, I can guarantee learning the same features up to some tolerable, say, ambiguities, then we wouldn't have these issues. Of course, the performance may get deteriorated a little bit under a new domain, but at least it would be consistent, not showing these wild variations, which essentially makes it more difficult to reliably deploy these models. A second related point is having disentangled representations. So from this identifiability view, let me consider my data generation mechanism is on the right-hand side, where I observe my high-dimensional data X, which is essentially, I treat it as a mapping from key latent generative factors denoted by Z1 through Zn through an unknown transformation, unknown complex mapping to the observed data space. So the goal of the disentangled representation learning fields, which essentially predates causal representation learning, the goal is there learning disentangled features such that every feature kind of corresponds to some semantically meaningful generating factor. In this toy example on the left, we have images of objects with different colors, shapes, and different backgrounds, essentially. And a good representation in this case would make sense that I learn a feature vector where each coordinate corresponds to a real factor of variation. So it gives us more interpretability, and it gives us more essentially control over the latent space. So the goal is then, we want to learn disentangled representations so that in the end, my learned Z hat 1 through Z hat n, they will each correspond to one real generative factor, rather than they are just an unknown function of all the variables entangled on the left. So to make it a more concrete example, which will be our running example throughout the talk, let's consider pose estimation from images. So this is actually not really considered until recently. This problem was not considered as a problem of the representation learning, but I argue that we can view it from that generative angle as well. So we have high-dimensional images, say image of a robotic arm with the multiple joint angles. And if I want to express this with only, say, phi factor of number of latent generative factors, which actually explains what's going on in the image, I don't need too many variables. Because say, first of all, like I can have the color or the length of the arms, etc., as latent factors as well. But since they are fixed from image to image, or even environment to environment, if I am using the same robots, what really matters, which captures what's going on in the image, is, say, learning the position of the joint angles. And these joint angles will be my understandable and at least pseudo-interpretable and low-dimensional representation. Of course, this pose estimation from images problem has a long history in robotics, with usually using supervised models. And recently, as in any field, machine learning has entered to this problem as well. And actually, a recent CVPR paper uses representation learning ideas to learn poses from images. So this RoboPep paper, which will be our SOTA comparison later, for instance, they use a self-supervised IGEPA backbone to learn features and then apply a heavy amount of supervised labels to estimate the poses from images. But is this pure deep learning approach without considering what are the ground truth relationships? Does it really capture the true generative factors? Because related to disentanglement, these, say, latent factors, they also have interactions between each other, among each other. So the equations do not really matter here, but just to give an example, robots' motions can be captured via a set of kinetic equations. And what really matters is if I change, for instance, like if I change the theta, like the phase of the joint angle here, from these equations, I can precisely track how it will affect the other latent factors. So they are actually not independent from each other. So that's why in physics, it would be ideal to model these variable interactions via a set of coupled equations, which might be simple or complex. So again, these coupled equations would tell us how these cause-effect relationships interplay in the latent space. And once we apply a machine learning algorithm, say I can learn maybe the statistical correlation between theta and x, for instance, just two of my random variables here. So I can do it in a data-driven way, but in the end, it will learn the joint distribution of these variables that I'm learning. So it might be good enough for, say, data generation or conditioning, or conditional data generation, say, but it will not tell me how these factors are really related to each other. So at this conjuncture, causal learning lies in between. So we will use causal learning as a both data-driven methods and also ideally, hopefully capturing the real generative factors. So just to recap, from these related fields, causal representation learning has emerged as their culmination of different fields and addressing the deficiencies of these different fields. For instance, in the disentangled representation learning, we generally have no theoretical guarantees in the, there's a flurry of papers from, say, 2017 to 2020-21 with different methods for how to make VAEs more disentangled, but they generally have very little theoretical guarantees. Or independent component analysis is a well-established field, especially closer to the signal processing communities as well. But there's those statistical interactions between the latent variables themselves are ignored. Everything's assumed to be independent. Or say the causal inference generally is thought as like developed separately from the machine learning, not benefiting enough from the data-driven techniques. So in causal representation learning, we want to combine the strengths of these separate fields. And everyone can have actually, like if you talk to a different CRL, I will use it as short for causal representation learning. If you talk to a different CRL researcher, they might have different views of like how to use CRL and how to interpret it. And in my view, I see it as a principled move from having good enough representations to learning ground truth representations, which can actually explain what's going on. And the way to do it is here where the causality comes into play. We enforce latent representations to follow a structural causal model to essentially have a rich representation space. So this will be the most, maybe one of the two most causal slides, so bear with me. In a structural causal model, we consider a bunch of random variables, say called system random variables, C1 through Cn. Each of them has an associated exogenous variable with some joint probability measure. And each variable Zi is assumed to be a function of a structural function of its direct causes, which we call parents in the graph, and the exogenous noise variable. So what does this translate to probabilistically? We can represent the joint probability distribution of the latent variable C as just product of the conditionals, where each conditional is only Zi given only its parents. So we don't need to add all the other variables. And we will call these conditional probability mechanism Ci given parent of Ci's as the causal mechanism of the variable Ci. So in standard causal inference and causal discovery literature, in causal inference, even the graph is given mostly, and in causal discovery, we are given data and we try to infer the graph, the DAG, directed acyclic graph, from the data. But in that standard literature, the variables are observed. In CRL, we actually learn these causal variables from more complex data. That's the significant jump from the observed causal inference literature to CRL. So to put it into a diagram, we have a latent data generation process where we have our latent variable C, which we want to learn, and unobserved unknown mapping, which we denote by little g, to the observed data X. And we perform our inference algorithms on the observed data X to estimate Z hat, our estimate of the latent Z, and also to form an estimate for their causal structure, capital G. And in the end, we can use our learned features and their causal relationships for whatever downstream objective we want to achieve. So the two big questions of the CRL is whether you can really identify this, like the identifiability question, which is algorithm agnostic. We want to determine whether a unique model, again, up to some tolerable ambiguities, whether a unique model can explain the data. And I hope it is kind of obvious that this is impossible if you don't make additional assumptions or if you don't use additional data. Because even in the on the left-hand side of the diagram, say if I change Z to some different Z tilde by properly changing my transform G as well, both of are unknown. Essentially, I can form any pair I want to generate the same data X, and data X is the all I see. So if I have only one IID samples from one data, like one latent data generation process, then there is no way I can invert it in a provably correct way. Related to that, the second aspect, which is say less emphasized in the literature but equally important, is how can you complement these identifiability guarantees you have, meaning that's how we can come up with provably correct inference algorithms. Of course, like if you have an identifiability result inspired by the theoretical derivation of the proofs, say, you can enforce it in your, say, favorite VAE framework or other inference algorithms. But for them to really provably correctly recover the z-hats and graph G, we need constructive proofs for identifiability. And I will show how using interventions and the score functions shortly, how we enable essentially combining the identifiability and achievability in a single path. So the conventional wisdom, again, to explain, to talk a bit more on why it is impossible. So if I just focus on, say, minimizing reconstruction loss, like minimizing this loss, then I can have infinitely many autoencoder. I can learn infinitely many autoencoder structures, which minimizes the loss all the same. But the loss functions which enable learning these ground truth variables will be significantly different. It will be an evolution of this, but it will have much more. So, what are some identification strategies to enable this data inversion process? So we need to, we can consider it as a toy example. So if you don't make any assumptions on the model class, then there's nothing really you can do. Like from the given data from a single space, there's nothing really you can do. But if you make more and more assumptions on the data generation process, meaning that, say, you can assume that your latents are Gaussian, or they are maybe independent as an extreme example, or they have some parametric structure, which many of the papers in the literature follow. So once we make these assumptions, we are effectively constraining the model class, all the possible models that can explain the data. Then I can get away with using maybe, say, less rich data observations. But in general, the richer your data observations are in terms of what kind of diversity they have, then easier the identifiability will get. So there are different approaches on how to provide the sufficient diversity to the data. For instance, we can use temporal variations, like observe a video and show how the causal relationships in the temporal setting become a little bit more obvious, but it becomes time dependent. Instead, we look at the interventions to provide this sufficient diversity in our data. And what do I mean by intervention? Again, I won't go into full detail of the causal descriptions, but to give one example from our running robotic arm example. So suppose consider some joint 4. In the observational domain, like if I don't intervene on the system, maybe the joint 4 can take values from like minus 0.5 to 0.5 radian. But I can do an intervention and change how the joint 4 operates. For instance, I can change its support, or maybe it's not taking uniform values, but distributed in a different distribution. So this effectively changes my whole latent distribution Z to some Z tilde. And although I don't observe it directly, I will observe it in my images as well. Like if I look at the distribution of the images, say I have some observational data sets, I do some intervention and collect some interventional data sets. If I compare them on average, they will differ. And this difference will be due to this sparse change in the latent space. So the point is, maybe in the observed high dimensional data space, on the pixel spaces, for instance, the differences will be very stark. But if you look at what is really changing, it might be really a sparse change in the latent generative space, which can be explained by maybe only one change in the joint angles. So that's the rough idea of how interventions might help. And to model the interventions briefly, so recall that we had joint factorization of my latent variables, where each causal mechanism was a conditional probability. So an intervention on variable I just changes that pi to a different conditional qi. So functionally, we can treat it as just changing the structural function fi to something different, f tilde I, or changing the exogenous noise variable in conjunction with it. So there are different types of interventions in causal literature. And for instance, if you talk to a more causal inference person, they might care more about the do interventions, which is essentially a deterministic change, saying I take one variable, I set it to a constant value. I don't care how it interacts with the other variables. But we are more interested in the stochastic setting, which we believe is more realistic and it can explain more scenarios. And here we have, again, two different types, where we have a hard intervention, which is a stochastic intervention, where Z3 is not set to, for instance, if I intervene on Z3, I'm not setting it on to constant value, but I'm setting it to a QZ3 distribution itself, that it is not affected by its parents, Z1 and Z2. Or I can have a milder intervention, which we call a soft intervention. Again, here the parents may be still intact, like Z1 and Z2 might still infect the generation of Z3, but their relationship have changed. Maybe they are their effect is softened upon my intervention, but not totally vanished. So I hope I'm not jumping too quickly between the subjects. But why interventions will be helpful to each other, will helpful when comparing them with each other, and how will they enable all these causal representation learning business? To show that, we need to, our tool is using score functions. So to recall, score function associated with some PDF PZ is given by gradient of its log PDF. And I will come to how the score estimation work a brief touch later. But you can tell that they, like, you probably know that score functions are at the center of especially diffusion modeling, diffusion-based, score-based generative modeling. So they've been attracting many people. It's an active research field. And what makes them enticing is, say, estimating the whole density of these, say, high dimensional complex maybe images might be really difficult. But estimating their score is somewhat easier. And then using Langevin dynamics, we can sample from those score functions to generate very realistic images. So how do score functions actually relate to interventions? So suppose we have, so this is stylized setting, but I hope it will make it clear like why the whole framework works. So consider two interventions on the same node. Like I target Z3 node, but on left-hand side, I have some Q3 mechanism. On the right-hand side, I have some Q tilde 3, but they are both only a function of Z3, like hard interventions. So if I take the difference of the log PDFs of the joint distributions, I can see that it becomes only a function of the intervened variable Z3, because all the other PI conditionals are untouched. So if I take their log, the factorization becomes additive and they cancel each other out. So, but this is a single scalar number. But if I take the gradient of this log PDF difference, then I end up with a vector which has the same dimension as my latent representation Z. And since this is only a function of the intervened variable, all the other coordinates, like the gradients with respect to the Z1, Z2, Z4, the rest of the variables, they will all be 0. So, which means if I look at my score difference function, difference of the two score functions coming from these two interventional environments, it will be a one sparse vector. So this sparsity will be my learning signal. So in the inference, I am effectively trying to learn some encoder H, which I pass my X through to generate Z hat estimate. So the idea is that for some H encoder to be valid, the score functions of the estimated variables should have the same sparsity structures as the true Z variables that I have just shown. So intuitively, if I apply a correct encoder, like the reverse of G, if I apply it, then I get the correct variable Z, Z hat equals Z, and these score differences of the Z hat across these interventions, it will be a function of only Zi. But if I apply an incorrect encoder, then there will be some entanglement between my Z hat 1 through Z hat n, which means if I try to factor its, like if I try to write the factorization of that Z hat distribution, and if I look at its score differences, it won't be a function of only one variable due to those entanglements. So that's the main idea we can promote this score difference sparsity in my estimated representation space. And the hope is that it will identify me, it will recover the true variables. So the loss function now becomes moving away from pure reconstruction loss, motivated by the sparsity property. We want to minimize the score variations across all different environment pairs. So is there any, like I said we can take the questions in the end, but it might be a little bit loaded. Is there any question up to this point? Okay, if not, I can continue. So to formalize, among all the possible choices of valid encoders, because my encoder should also have an associated decoder, I am not considering just a random function. The true encoder will induce the smallest aggregate score differences in terms of the sparsity when we say small. So from this view, by just minimizing this loss function, I can identify some H star. Now the rest of the talk will becomes okay, what are the conditions really where there exists a unique, again up to some specifications, some unique H star. And we show that up to this point, using the score functions, we can come up with the objectives which provably identifies the true encoder, so that we can effectively reduce the CRL problem to score estimation problem. So if you estimate the scores perfectly, and if you give me sufficient data which ensures that your H star is unique, then this objective and variations of it tells you exactly what is your algorithm to run in practice. But we have made too many technical simplifications. So this was our objective function. First of all the nice properties we talked so far are based on latent score functions, which is by definition latent, inaccessible. How do we really access that to use it in our learning objective? And how do you really even estimate these? Also, for this objective, I use 2 hard intervention per node and compared them. What if I do not have 2, but maybe only 1, which might be very well the case in practice? And again, we have assumed hard interventions, but in practice, it might be difficult to ensure that you have hard interventions. Can we work with more relaxed notions of the perturbations to the system in the form of soft interventions? So in different papers, we address these different aspects. But to begin with, the most obvious one, how do we even access the latent score functions? we make the nice observation that actually you can compute the latent score differences, not the score itself, but the differences using observed score differences. To see this, we can write a change of variables between the px and pz and take its gradient. And note that the second term, this gradient with respect to this log term, this is shared across different, like this is not affected by which distribution you are sampling from. It just takes, G is fixed, my transform is fixed across all the distributions. So if I write this for two separate interventions and take their difference, then the second term will cancel out. And this Jacobian of the decoder, the true decoder G term is shared. So my score difference of Z can be exactly written as score difference of X times some Jacobian term, which can be, again, just computed from data in a data-driven way. So note that now SC is unobserved, but my X is observed. I can apply score estimation techniques from all those generative toolkits. And how, so, but this is for the true latent variables and the true observed data. How do I use it in my algorithm? In my algorithm, my objective is based on the score of my estimated Z hat. But I can write the same relationship between Z hat and SX as well. In the end, they are just related by, again, Jacobian of my candidate decoder, which I can compute via autodiff in standard libraries. So this tells me, given data, just compute the score functions of the observed data, their score differences. And I can immediately plug this right-hand side term to my objective function, which gives me the latent score functions. So coming back to our stylized but general setting, we consider two hard interventions per node. And the interventions are affecting only a single variable. And we do not worry about the score estimation will be perfect or imperfect, because all the identifiable results, they start with assuming you have an oracle, whether it is even possible to solve it if you have, say, a perfect score oracle. But in this case, the beauty is that we don't make any other assumption on the data generation process. We don't constrain the causal model. We don't constrain the transformation from latent to observed space. They can be both non-parametric. And using the sparsity property that we have just derived a couple slides earlier, we can show that by minimizing this objective. So suppose you are given data from only two environments which target the same node. Just compute their score difference and make sure that the expectation of this score difference will be a one sparse vector. And this enables perfect disentanglement, meaning that every Z hat I will be a function of Zi only. For the sake of time, I skipped some derivation details, but just to give one background, in the first version of the paper, we had rather lengthier proofs as in the similar literature. But in the end, we actually realized that this can be a much simpler derivation by, again, just connecting this score transform between any given two distributions, like how they relate to each other, and using the sparsity properties, the Jacobian of the transform, this phi transform, should be sparse, which gives us the identifiability in the end. So what if we have only one set of interventions? And so far, note that we only talk about recovering the latent variables. But in the beginning, I motivated my work by also saying we can recover the causal interactions, which are captured by the latent graph. So how do we recover the graph? So we revisit the concept of score differences, but this time with the intervention on the left, we are comparing with the observation data on the right. And note that here, Z3, its parents are still intact here, which means if I take score difference of these two distributions, I won't get one sparse, but I will still get a sparse vector where the only non-zero coordinates are just corresponding to parents of the intervened variable. This means if I have the true score differences, I can immediately read my graph by looking at these non-zero coordinates. I tell, okay, this is my intermediate node, and the others, other non-zeros are the parent coordinates. Life is easy. And since we have shown you how to recover the true Z using the score-based loss function, in the end, instead of using two sets of interventions, I can just use one of them to derive my causal graph in the end, which guarantees that I can recover the graph exactly. So to summarize, in the general setting, oops, I probably some mistake in the copy paste. So in the most general setting, where the transformation is non-parametric, no assumption, and the latent causal model also non-parametric, no assumption, using two hard interventions per node, I can recover the graph perfectly, and I can recover the variables up to some component-wise transform. Only element-wise. Each variable is only a function of a true latent variable. So to show an application of it, I turn back to the robotics example and say we want to do what the RoboPep paper did in supervised setting. We are asking the question like, can we do it in a unsupervised or a very weakly supervised case? Like we want to apply these CRL ideas to learn the joint angles of a robot from the images. So in our recent NeurIPS workshop paper, which will be presented next month and also under submission, we look at this problem. So there are some more technical details about how to make this work in practice, because of course, like I say, the objective is provably correct. It gives a provably correct algorithm. But in practice, of course, we need to shout some details to make it work. So for instance, instead of using a single autoencoder, we use two autoencoders such that we first do sort of a dimensionality reduction so that we can have a more amenable feature map that we can, like a mid-step feature map that we can handle easier. So on a very high level idea, the first autoencoder, the dimensionality reduction part, is trained for ensuring there's good reconstruction. In the end, I can reconstruct the given robot arm image. And in the middle part, the second autoencoder is optimized for minimizing the score variations given interventional data from different robotic environments. So to show how it works, I first cite the results of this recent CVPR paper. In the supervised setting, we can look at the just mean squared error in the angle estimation, joint angle estimation in the radian. And we can see that if we use, by the way, here when we say 100% of labels, so say for learning the representations, we need to use many thousands of samples to learn good representations in an unsupervised or self-supervised way. So we vary like how much data the supervised methods really needs to learn really good joint angles in the end. So we see that like if you use all the data, which was, if I recall correctly, over like 200,000 samples, you get very good results from just estimating the pulse from images. But if you lower the percentage of available supervised data, here supervised label refers to knowing the exact labels for the training set. If you reduce the numbers of the supervised samples, then obviously the performance gets worse. So enter the our CRL-based ROPS framework, which is robotic pose estimation via score-based CRL. We see that using no labels, we get very, very close results, say using 5% of the labels of the whole supervised framework, which means supervised frameworks require too many samples, like require huge amount of samples to say outperform our unsupervised approach. So I maybe should add that I'm not a roboticist, like I'm not really an expert in this field, but I believe this demonstration shows that. So this is a well-established problem in robotics, even pre-machine learning techniques. And there are supervised machine learning techniques. And what we show is opening a new road, saying that we can solve well-established robotics problems using CRL, not replacing the existing methods, but providing an alternative, which might prove useful in, say, data constraint settings. And we hope that this might give, this might have influence on solving other related problems. So these were all, and obviously in the robotic setting, the image to latent transform, it is highly complex, essentially an image rendering process, which we cannot fully parameterize. So coming back to the interventional CRL landscape, in the very beginning, I have said that the extent of the identifiability depends on what kind of assumptions you make. And in the previous setting, we didn't make any assumption on the transform or the causal model. But in literature, you can make different assumptions on the mapping. We can make parametric assumptions, or more importantly, what type of interventions you might really have, because we can consider, say, unknown targets. Like in practice, if you are given some data sets, it is difficult to guarantee that the interventions are happening on a single variable. Surely that might be the intention of us. That might be a sparse change, but still it can be affecting more than one variable. Or it might be a softer intervention which doesn't fully remove the effect of the causal parents. So in the next, I will briefly touch on the limited time. By the way, how much time do I have? Like 10 minutes or longer?
Yeah, actually, if we can limit it to 10 minutes.
Okay. Then I will go very quickly over just touching on the nature of the results. So if we consider a linear transform from latent to observed space, meaning that my G transformation now becomes a full rank matrix, then I can solve a bunch of different problems. For instance, I can consider only one intervention per node, and I can consider soft interventions. Again, I am skipping like the algorithm design perspective, but in the end, I say that using only one hard intervention instead of two, I can get up to scaling recovery. So previously, we were just disentangling, saying that my z hat I is a function of zi, which is good enough for many settings, because in the end, I will have some downstream component as well. But in this linear setting, leveraging the parameterization, we can get much better and just say we get z hat, we recover the latent up to direct scaling. And if we have the soft intervention, things get a little bit obviously more difficult. But we can still show that we recover the graph up to transitive closure, which means that we may not get the graph exactly, which is actually known to be impossible by prior results, but we can still recover all the ancestral relationships, which is still useful, because like if you know which variable might have somewhere on the downstream effects on another latent variable, then it is still useful information. And I can recover the latent variables up to mixing with parents, meaning that so it may not be only a function of true zi, but it is a function of only a few variables like zi and its direct causes. And again, here we make no assumption on the latent causal model. that if we are willing to make some nonlinearity assumptions, we can even get better results. Say we can exactly recover the graph, or we can ensure some Markov properties on the latent variables. Okay, skipping those. So for the multi-node intervention setting, again, discussions so far are saying every data set, only one variable is being affected by my intervention. But I can solve the multi-node intervention case as well. But the challenge here is, so the score differences when comparing two environments, two joint distributions, it won't be sparse anymore because many nodes might be affected. Their parents may become all non-zero. I might not have sparse vector in the end. So the question is, like, can we still guarantee, like, under what conditions we can still have theoretical guarantees using these multi-node interventions? And our idea is these score differences, they are very modular. So if I can combine them in, say, I take multiple environments and I compute their score difference, if I can find a way to aggregate them to create sparser interventions, I can effectively reduce the bigger problem to a problem which I have already solved. But of course, the algorithm design here requires many tricks, but in the end, long story short, I can recover the same I can ensure the same identifiability guarantees when given enough multi-node intervention targets. So this is not a deal breaker. So finally, in the score estimation touch, there is growing interest due to, again, the widespread applications in the diffusion models. So since this is not my main field of research, I won't go into details, but just saying that there exists various consistent estimators, which can be parametric or non-parametric, like RKHS-based, or just using a cross entropy loss to learn the log density ratio, which I can take the gradient later to get my score difference. But so far, all the guarantees were on perfect score estimation. Even though these score estimators are consistent, in practice, of course, I have finite samples, which means my score estimates will be imperfect. And do these imperfect scores break my algorithms, or can I still have some guarantees? So motivated by some sensitivity analysis showing that our experiment results are actually somewhat robust against noise, meaning like if I change the signal to noise ratio, then this is a very simple demonstration. I hope the details, obviously I don't have time to go into details, but just showing that if you increase the signal to noise ratio in your score function estimates, then you get almost perfect graph recovery. And obviously with with increasingly many samples, we hope to get better recovery. And in our NeurIPS paper, we established the first study on sample complexity for CRL. So given, in the sense of probably approximately correct guarantees. So just to recap with one sentence, if I have a consistent score difference estimator, again, which is given to me, which exists, then I can guarantee that with high probability, I will recover the same identifiability and algorithmic guarantees using this finitely many samples. So to recap, I went over our score-based CRL proposal, essentially, in which we can accommodate various model settings. We can accommodate different data settings where the nature of interventions change. And beyond going to identifiability proofs, it helps us design provably correct algorithms. And we hope that we are just scratching the surface on unlocking applications in physical domains such as robotics. But of course, the big question is, even though we have some sample complexity guarantees, the score estimation, we are still using like the borrowing tools which are developed for other targets. say those score estimation techniques, their success is generally just measured by like how realistic are the images that's being sampled from those scores. But here we have a very, very specific structure. Essentially, we are estimating the score differences on lower dimensional manifolds. It's an interesting theoretical question that I hope to look at in the near future, like how can we make this CRL specific so that we can improve the performance. And to mention a few feature directions, I have told you only the interventional story, but as I mentioned, there exists different approaches. Like there are different ways of inducing diversity in the data. Suppose if you have two different camera viewing the same view, it gives you multi-view data. Like how to combine these different approaches to say reduce the requirements. Say maybe instead of requiring too many interventions, I can get away with very few interventions if I augment it with additional information. And so I'm skipping the middle one. One area which I'm excited about, actually I'm not involved, but my collaborators have upcoming NeurIPS paper on that. Can we learn only what we need for the downstream tasks? Meaning that right now we are just focused on learn the true representations. What will be the downstream task? What will be the utility in the end? We don't care about it. It's the task of the practitioner. But if we want to say maximize the utility and learn the representation, like learn the true representation, which will be needed to maximize this utility. If we can learn them simultaneously, then it can combine multiple seemingly different fields in one pot, and I believe can be more realistic. So I have given you some example on robotics, but there are different directions to pursue in, it's not my field, but there are some groups which are trying to apply CRL ideas to gene regulatory network. And there are studies to model, like how can we model the underlying factors behind the natural language that we see, so making connections to LLMs. And personally, I just want to finish with saying, so this work was essentially last 2 years of my PhD and some more during my postdoc. Very recently, I'm looking at more broader identifiable representation learning directions, because we see so CRL suggests a paradigm shift, essentially giving a new model, a new way of learning representations. But even in the current way of doing things, there is a growing body of evidence for showing that we actually might be learning some converging representations. Say different modalities, if you use similar learning signals, then you might end up with matching representations in somewhat of a recoverable, invertible way. But there do not exist too many theoretical explanations, but one recent ICML paper we tried to understand what's really going behind, or is there something identifiable on especially self-supervised learning. So these two approaches seem to be at the surface different from each other, where CRL focuses on identifying the data generation process, where the other like identifiable representation learning approaches try to say improve or analyze the objectives in the current mainstream pipelines. But in my view, like they are not too separate from each other. So I don't have concrete results to talk about yet. Hopefully in the future, maybe next year, I hope to have more to say about the connections between those different representation learning paradigms. So that was all. I hope I didn't go too technical on the causal side. And I realize I probably need to reduce the content a little bit to fit into time limitations. If you have questions, I'd love to answer.